Well, thank you very much. There's been a lot of discussion recently about the importance of identifying critical metals, mineral systems in the Mount Isa or Northwest Minerals Province. And what I want to do in this presentation is take you through a little bit of the learning curve that I underwent in terms of understanding the systems. And it started with firstly doing some work for Chinalco on Lane Dorothy and Blue Caesar, then subsequently compiling a report for the Mines Department on cobalt and heavy rare earth mineral systems, mainly in the Cloncurry area, taking largely historical data sets. And then finally, working with Transition Resources, a private company with a fairly large tenement package in the Cloncurry area on a new discovery that we've made of quite a significant cobalt and rare earth system, which we've called Highway. Can we take that screen off the bottom of the piece? And what I show on this this first image, in the top image, if I can use, yeah, that's good. Yeah, yeah, that's cool. That's right. Yeah. Okay, go back to. Let me go back. Get back.
Use the arrows now.
Yeah. I'll go back to the first slide. Go back to the first slide again. Right. Okay.
Yeah, so just use those.
I will. Okay. On the top image, on the right-hand side of the screen, is a thin section from Mount Cobalt. These samples were very kindly provided to me by Vera Munro Smith, who did a PhD in the 1980s on cobalt mineral systems in Australia, and she had a number of very, very important historical samples from the waste dumps which used to exist at Mount Cobalt. And I was able to utilize some of those, and it shows a very nice example of erythrite from the Mount Cobalt system. The bottom sample on the screen is a discovery sample from Highway. It contains 900+ million cobalt, 28 grams a ton gold, 1000 ppm tungsten. It's high in nickel, high in scandium, 600 ppm yttrium, 150 ppm dysprosium, and 92 ppm ytterbium. Now, this is clearly a very, very interesting and critical metals rich sample, and it contains visible gold. So what I want to do in this presentation is take you through a little bit of the exploration rationale that we used. It's based on some work that Peter Betts did initially on the reconstruction of Western United States, or Laurentia, with Northern Australia, suggesting that there may be a link between the Idaho Cobalt Belt and some of the mineral system terrains in the Northwest Mineral Province. I'll give you some examples of heavy rare earth and cobalt bearing systems that we worked on in the Cloncurry area. I'll then discuss the implications of some of the textures that I saw, which are very similar to textures that I'd seen previously in Fiji and also in the Avalon Peninsula in Newfoundland on epithermal systems. I'll then talk about the constraints on these mineral systems based on the transition metal abundances and the highly siderophile element abundances, namely the platinum group metals, rare earth patterns and geodynamic, and then very briefly, the Highway discovery. The image here is taken from a paper by Carl Collerson, 2001, showing the Western United States Australia reconstruction with a suggestion made by Peter Betts of a possible link between the mineralization that we see in the Gawler Craton with the Mount Isa area, and then extending into the Idaho Cobalt Belt, which was this point was made by John Slack when he finished a paper in 2012 on rare earth systems in the Idaho Cobalt Belt. In Idaho, there are substantially enriched, very significant heavy rare earth rich mineral systems. These are chondrite normalized plots, and we use chondrite normalized plots to smooth out the Otto-Harkins effect, which is the various abundances of high atomic number to low atomic number elements as you increase atomic number. And what we see in this image, if I can get here. You see, these are very, very elevated in heavy rare earths. They also show a negative europium anomaly and non-chondritic yttrium-holmium ratio. And that's critical because that indicates fluid-dominated systems rather than the effect of plagioclase fractionation, which people normally consider for these europium anomalies. We also see here from one or two of the other Idaho cobalt belt very substantially enriched heavy rare earths. That's the typical xenotime rare earth pattern. A very useful plot that was produced by Lubert and Alaig in the 1970s shows the distribution of different rare earth bearing systems based on their rare earth and their high rare earth, heavy rare earth to light rare earth ratio with rare earth concentration. On this, we see carbonatites with elevated lanthanum ytterbium ratios. They're very light rare earth enriched, whereas hydrothermal rare earth systems tend to be more enriched in the heavy rare earths. So when we see a heavy rare earth dominated deposit, we know it's a hydrothermal or carbothermal based system. The areas that we looked at in the Cloncurry region are shown here in green. I looked at samples all the way from Mount Cobalt, Barnshaft, Mount Frieda, Iron Duke, Evening Star, Jewel and Shamrock, Gilded Rose, up as far as Salisbury and Monacol. We also looked at material from Elaine Dorothy and also Millennium, but the most important samples that we looked at came from Mount Cobalt. And here are some examples of Mount Cobalt samples. The first one is an ultramafic schist, rich in cobaltite, about 9% cobalt, high concentration of nickel, elevated copper, 5 ppb palladium, 2 ppb platinum, and 1 ppm gold. The second sample is an erythrite-rich system, high in scandium, elevated platinum, palladium, gadolinium, dysprosium, gold, 11 ppm, very high total concentration of rare earths, 0.6%, elevated concentration of heavy rare earths and yttrium, and a very, very high heavy rare earth to total rare earth ratio. The second sample is a very unique sample. It's undeformed, preserves beautiful, for those that have forgotten what petrology is, and that seems to be going out of fashion these days, but this shows a very nice image of a plane polarized light photomicrograph in the top panel and a cross polarized light photograph in the bottom panel. Beautiful pseudomorph pyroxene in a serpentinized olivine matrix, undeformed, clearly post-tectonic, nothing to do with any deformation event. And this is an igneous texture preserved in olivine peroxenite. And this is a very important observation. This sample contains economic grades of scandium, 270 ppm scandium. It's high in cobalt, high in nickel, high in copper, chromium, yttrium, gadolinium, and dysprosium. It contains almost 3% total rare earths and yttrium. It's clearly a very economic sample. There's another sample of serpentinized olivine-bearing peroxenite. This one contains 24% cobalt, high in nickel. The story is the same. These samples are elevated in the rare earths as well as in the transition metals and in the precious metals. A sample from over a little bit further north from one of Osmex's tenements in the Iron Duke system, we see the same pattern there. High copper, high cobalt, scandium a little bit low, but rich in gold and rich in platinum and palladium, but with high tellurium. That's an interesting observation because these telluride bearing samples are very, very unique, and they're suggesting that we may have epithermal textures, suggesting something very important about the paleo environment at the time of mineralization. This sample also is extremely rich in yttrium, gadolinium, dysprosium, lower concentrations of light rare earths. Total concentration of rare earths in this sample, 1.5%. And it's dominated by the heavy rare earths. Very interesting. I just come back from Fiji, where I've been looking at epithermal textures, and I spent a lot of time on the Avalon Peninsula in Newfoundland looking at epithermal textures. And it struck me that there were systems in the Cloncurry area which were highly suggestive that we may be preserving in this area some epithermal textures, and particularly this one on the bottom right-hand screen. That's a classic example of silica replacing carbonate with coliform layering and bugs of druzy quartz, a classic epithermal texture. In thin section, we see nice examples of coliform quartz intermixed with goethite breccia that is heavy rare earth rich. Now, the highway discovery is an outcropping discovery. The tenements were held by Gold Search, who didn't find gold. This sample contains 8 ppm gold. It's a breccia. It's highly enriched in the light rare earths and the heavy rare earths. Total concentration is 0.5% total rare earths plus yttrium. The heavy rare earth yttrium concentration is 3,500 ppm. It's quite a unique system. It's also rich in cobalt, nickel, scandium, platinum, and palladium. The rare earth patterns are shown here. It's dominated by xenotime and monazite. And when you get a mixture of the xenotime and monazite, you get essentially flat rare earth patterns. This is one of our examples taken from some recent drill core that we analyzed last year, but it shows the classic rare earth pattern of xenotime with monazite. It also shows the negative europium anomalies and the negative and the non-chondritic yttrium-holmium ratios, suggestive of fluids. And some other examples from Barnes shaft, slightly different. Barnes looks more like an alkaline type system, possibly with some component of an A-type granite contributing the rare earths, but with the very distinctive negative europium and negative yttrium-holmium ratios, showing the effect of fluorine fractionation. Elaine Dorothy, patterns are shown here. They look very much like the patterns we see in alkaline intrusions like the Gardar complex in Brazil, or closer to home, like we see at Mount Ramsay in Queensland. Once again, negative europium anomaly and non-chondritic yttrium-holmium ratios. When we look at Mary Kathleen, this is a large data set that was analyses provided initially by Chinalco, plotting nickel, cobalt, and nickel copper. We see here a very, very extensive field with elevated nickel, elevated cobalt, elevated nickel, elevated copper. These are not the sorts of patterns that we would expect from a granitic source. These rocks are suggestive of a mafic to ultramafic source, possibly similar to the source that we saw at Mount Cobalt, and certainly not from the burstal granite. When we look at the highly siderophile element patterns in Mount Cobalt and Iron Duke, they more or less match the pattern that we see for the Mary Kathleen system, and suggesting a mafic to ultramafic source rather than a granitic source, not a crustal granitic source. When we look at the distribution of this data on a typical plot of light rare earth to heavy rare earth ratio against total rare earths, the Mary Kathleen system appears to be trending from differentiated mafic to ultramafic compositions more into the carbonatite field. It doesn't lie within the A-type granite field. We see in the Mary Kathleen system evidence of feldspathoids. This is lucite and this is melilite. These are in some of the drill core from Elaine Dorothy. We also see in the Mary Kathleen system evidence of potassic ultramafic rocks in the form of lamprifiers, ultramafic lamprifiers, containing pseudomorphs of talc after olivine And when plotted on the potassium sodium projection against magnesium, they plot in the ultrapotassic field. These rocks were missed. They were logged as pylitic schist. When we look at the distribution of our highway discovery, we see that there are essentially two trends in our data. It's quite an extensive data set. This is the analyses we did last year. We see a trend extending from possibly the source compositions towards a carbonatitic component, but we also see the effect of the fluid-rich exsolution vector taking us over into the sweet spot for rare earth exploration, for heavy rare earth exploration, the carbothermal field, which is enriched in the heavy rare earths. When we compare the data from highway with the data from the Merle system in the Idaho Cobalt Belt, they're virtually identical. And this is an example of one of our xenotime grains that we dated from highway. And notice the age, 1530. So the Idaho Cobalt Belt and the suite that we have from highway are virtually identical. So basically the source of metals, although Williams suggested they possibly came from the Williams-Naraka Granite Association, the element association we see here is totally inconsistent with a felsic source. A more plausible explanation is they come from a mafic and ultramafic source, possibly similar to the peroxenites we saw at Mount Cobalt and in Mary Kathleen. And clearly the granites failed the fertility test. Thank you.
Thanks, Ken. Do you have any questions for Ken?
Yeah.
Yeah? All the other side, David. Off you go.
Can I get a drink of water? Just,
Yeah, please.
Thanks, Ken. Really interesting stuff. I'm just wondering if you can comment on the tonnage potential at those kind of grades.
Watch this space. We're drilling at the moment. We have 4,000 assays waiting to get back. We have a drill program we completed last year. We have done a preliminary resource estimate based on our gold concentrations, but that's not public information at present. And as we're a private company, we can't, we're not willing, it's not necessary to divulge that at the moment, but it is included in some of the Mines Department reports that we have submitted.
Okay, so, but if you were to compare these systems to say, or you were saying that the Idaho Cobalt Belt was an analog, what are the tonnages that you see in these kind of systems? What scale are they at?
All I could say is the Idaho Cobalt Belt has been completely overlooked as a rare earth source. The paper by John Slack, which was published in Economic Geology in 2012, highlighted the potential importance of the Idaho Cobalt Belt for exploration, but none of the other companies that are actually going into Idaho working at the moment, and that includes Jervos and a few other companies, have actually focused on this point yet. It's gone under the radar. So Idaho Cobalt Belt is a very good example of a place to go to get tenements to find a heavy rare earth deposit, because the light rare earth deposits, the deposits that are rich in neodymium and praseodymium, they're a dime a dozen in carbonatites. The heavy rare earth deposits are much rarer. The main source of heavy rare earths comes from Chinese sourced ionic clays, which are generally low grade, cause the extraction causes huge environmental damage. The preferred source of heavy rare earths would clearly be a hard rock deposit. And there are a number of examples. In the Western Australia, Northern Minerals has a very good system in the Tanami, but they're really quite rare. Yeah. Joe.
Thanks, Ken. That's a really interesting talk. Very interesting because from the hydro work that we've done, we've picked up a lot of potential nickel in a sort of areas. And I think your work just confirmed that, you know, it's real. I really appreciate it. Thanks.
Thank you.
We might have one more.
Thank you, Ken. It's really amazing combination where you have platinum group elements and rare earth. I was just wondering, do you have an idea on the mechanism how you get this and you infer it's you know, mental derived sources, ultramafic rocks? Is a possibility, I think, if you have two different processes where you get one sweet like platinum group elements is one sort of mechanism, and you have your rares with sort of a different system contributing, because I struggle to get, you know, all these metals and rares as one single package.
That's a very good question. And I skipped over one diagram there, which was a sort of a tectonic interpretation of niobium-yttrium ratio versus niobium plus yttrium, and it was a plot that was produced by Joe Whalen and Bob Hildebrand, who work in the Western US, looking at the role of slab tears and plumes and in an arc magmatic system. And clearly our data, as their data showed from the Western US, is that many of the systems that are potentially fertile for transition metals are those that have been affected by a slab tear, which has enabled a deep source component to get in that's niobium enriched in the suggesting of a plume component. So I think what we're seeing is possibly several components in this mineral system, a deep source component, probably an arc component, and possibly an enriched mantle wedge component combining to produce the metal source for this system. And then superimposed on that, we have the effect of late stage fluid exsolution producing our epithermal systems. And you know, that example of the silica replacement of calcite is just an absolute classic example of a high level epithermal system. And that has great implications for, you know, if this system is 15, 30 million years old, what it's meaning is that this land surface there has been awfully stable for a long period of time.